Joel. Yeah.
Hi, Joel. Thanks for joining in. This would be great. Okay. So I hope you can see my screen, right? It's visible. Um,
Yes.
yeah, great. Okay. Though I thought of kind of reading the kind of paper in detail and try to cover, understand each and everything, but I think it was too short of time for me to kind of go and look at everything in detail. So of course there would be some shortcomings. So let's just see how would I do it. Yeah, and then please correct me, all the authors who are on the call to um, take it forward. Okay, so this particular paper was published in the KubeCon, I think a week and a, I mean last week, I believe, uh, and this particular paper, as the name suggests, is cloud native artificial intelligence. So it's kind of convergence of cloud native and AI. That is what is here, and what this particular paper talks about is basically there are, of course, certain aspect of technology which cloud native supports, and which is there to kind of run all the AI ML workloads, but there are still challenges and gaps which are remaining to kind of fulfill. And as a part of the charter of the cloud native foundation, right, cloud native CNCF found there, right, we want to make sure that we fill that gap, and then have the AIML workloads as a first class citizen on the cloud native um, landscape there. So it talks about challenges. Apart from that, of course, talks about what is already there in the cloud native um, ecosystem, so that it can support the workloads there. Um, so first of all, this book starts the chapter or the paper starts with kind of covering a brief intro about cloud native. So I think we all know about it: Docker, Wave, Kubernetes, and we are all here right now. And this is the definition of the cloud native. So I think I'll not go in this particular session, but I assume that all of you would know about it. But let's talk about the cloud native AI in evolving is an evolving extension of cloud native. So I think I see that as kind of things are evolving, and what I see as per my reading there, right, that companies are going to put the whatever the models they are building, the private models, they need some way to build it, and of course execute or serve them. And for that purpose, they would require some way to kind of execute or something to put the workload on, right? And then cloud native technologies like Kubernetes becomes kind of a default choice there to kind of run that workload. That is what I see. And that is what kind of I believe mentioned here by combining the cloud native and AI together, which refers to approaches and patterns of building and deploying the AI applications and workloads using the principles of cloud native. So, and by doing that, you will enable repeatable and scalable workloads um, um, on top of the Kubernetes ecosystem there. But I would have this question. I think it's been answered briefly later as well, and I need input from the authors here. That as the existing AI practitioners, right, they would be having their own workflow, right, writing down all these notebooks and so on. Why would they kind of come to the cloud native ecosystem, right? And basically, why would they kind of prefer? So if they already have a workflow, why would they kind of come and adopt the cloud native way of doing things, like learning about pods, learning about Kubernetes, and so on? So that was one question I had, and it's been briefly answered later by kind of making the cloud native tool such that it kind of supports the ID, it kind of supports the transparent or kind of transition from notebook to the Kubernetes deployment in one go. So that's kind of briefly answered there. But if the authors want to kind of put some more lights on that, that would be helpful.
So, Adel, I'm not sure if I can answer, but I'm not an author, but I'm sort of new to their group. But the reason they come and use Kubernetes is because Kubernetes. So when we use these AI-focused workflows, they use GPUs, right? But GPUs requires drivers. Now, when someone like a data scientist or someone who's conversant with AI workflows, you can't expect them to sort of know about drivers or take the effort of sort of configuring drivers and so on. And that's where Kubernetes comes in. There are drivers, there are daemon sets that can, make this so simple that they can focus over their AI workflows. And it's not just over installation. When we run AI training, AI inference models, okay, what happens is we need more or less capacity. These are expensive, right? GPUs are expensive. So we need to scale up, scale down. And Kubernetes has ways like, like there are open source things like Carpenter and all that help understand the workload requirements and can scale up and scale down. And that's where, Kubernetes makes a huge difference, that they don't have to focus on the infrastructure. They can focus over the AI workflow, AI sort of, the AI part of it instead of, infrastructure.
But sorry.
Go ahead, Nipandra.
So, but that would already be in place now, right? So, for example, if somebody is developing the AI solutions right now, right, they would be doing some way right now anyway, right?
Yes and no. So yes, they would be right doing it, but then they would have to know it to do it, right? So this sort of abstracts it, and this takes away all that effort. Because think of it like think of it someone deploying doing some AI training. Okay, the person or the group of people, they want to focus on their AI training model, not on the underlying infrastructure, whatever it may be. It may be Kubernetes, it may be VMs, it may be bare metal, and so on. So the moment we have things like Kubernetes that manages scalability, that manage, okay, if one pod is down, okay, I can bring up another pod. They don't have to take care of all the infrastructure level things, and that makes a big difference in terms of time and effort, in terms of deployment, and in terms of cost also. When things because Kubernetes, because of the open source sort of ecosystem, has has ways where you can sort of configure it using simple YAML files on what should we do. Okay, should we wait? When a training model is sort of done with its thing, should we scale down? Should we scale down after some time? We just have to do it all this instead of having to worry about about costs and all. You just have to configure these basic parameters, and that's it. Kubernetes is going to take care of it. There's no need there's no much need for someone who's using ML workflows to sort of take care of the underlying infrastructure. And that's where I think cloud native and Kubernetes makes a huge difference.
Yeah.
Hey, Vijay, quick question. I'm trying to figure out how is development and the production works, right? It feels like the way you're explaining is once it is in production, you deploy it in Kubernetes. Is that the right way of understanding what you're saying?
Sort of yes and no. I mean, yes, production we can deploy in Kubernetes, but then ideally production you would like to simulate it in test environment also, right? So even in a test environment, and when we talk about AI training data, they are like long jobs, long running jobs, sometimes hours, sometimes days, sometimes much more. So yes, I mean, in an ideal state, we would like training or the test to be as close to production as possible. So I would say this is applicable for test also, not just production. Adele, I don't mean to interrupt in any way. Okay, just trying to help.
No, all good. I was just going to say, so to answer the original question, not everyone needs cloud native Kubernetes and technologies, right? So if we divide the personas, I mean, I like that you showed the figure here because we have predictive and generative AI and predictive AI. And sometimes if you divide the persona, you'd have the data engineer and the data scientist. Usually if you're developing locally on a laptop, all works. You have Docker. You're building. You're training the models using scikit-learn. You're even doing it on CPU. All the things are nice and green and happy. The problem starts when you have scale, similar to any other application, and then you start to need. Okay, so how do I orchestrate my workloads? How do I make it immutable? How do I make it reproducible? And so the same problems that Kubernetes and the cloud native landscape have been trying to solve, whether it's building a set of APIs to declaratively say intent, or to schedule workload in the right nodes and the right, on the right infrastructure, and the plumbing that is needed towards that. So we have been doing a lot of effort in the cloud native landscape for quite a long time to solve for the problem of scale. So scale here is important. So if you're running it on a local machine, it works. But once you're training large models, you need distributed training. Things like jobs start to appear. How do I distribute? How do I share the infrastructure, the GPUs across the infrastructure? All of these are problems that are not apparent in simple model training like predictive AI. With generative AI, the landscape is a bit changing. They're called large models, right? And so large models means large big data, basically. So you need to orchestrate data. You need to orchestrate the jobs that does the training, and then of course you need to abstract all of that away, so that as a data scientist that doesn't know about infrastructure, they have the right APIs to declaratively state what they want. But also, even Kubernetes might be hard, so they might not even know. But it would be the base for the platform that the machine learning engineer built. Then also the infrastructure or the platform engineer, they also don't know about modeling. But they want to build on solid abstraction. So the cloud native landscape provided us with projects like Knative for serving, not just model serving, but serving service mesh for abstracting away the network and the application layer, and so on. So these are all projects residing in the cloud native landscape that help us build abstraction using them for data scientists to say, I want to train jobs. So for you to be able to build abstraction, you need a solid foundation, and that foundation can be all the cloud native tooling and orchestrators that we've been building, whether it's single cluster, in cluster, or multi-cluster scheduling. So this is basically, why you would need cloud native, and why people building models at scale would need something like, cloud native and Kubernetes. Not everyone does. If you're just doing it for, a team of 2, 3, 4, and you're just building predictive AI models and classification and regression and whatnot, you typically don't need that complexity. And that complexity is needed only when you're at scale. And complexity is justified. It's actually there to simplify your life.
Yeah, makes sense. And of course, one more point which I just thought of, that I believe most of the consumers not consumers per se, who is going to uh, so developers are going to build the applications on top of the LLMs, what is there, right? And the developers may not need to know about what is happening behind, right? And then if the solutions are being served by Kubernetes, which has everything, developers just kind of go and kind of build the applications. Like once we figure out which model to use, and we just try to wrap around it. For example, if you have to kind of build an application which kind of uh, takes a folder of images and classify them, then as a developer, I just want to build my wrapper around whatever that stream data, whatever it is there, right? And that's when things are taken care by the provider there. Okay.
So I think a developer doesn't need to know about Kubernetes,
yes,
right? And that's the problem we're trying to abstract away,
yes.
like for platform engineering and developer portals and whatnot. But the base, the foundation that makes us able to abstract away all these details is things like Kubernetes.
Yep, correct. So while we are here, sure, go ahead.
No, I had a quick question. Somebody needs to know about Kubernetes, right? So is it that data engineer, data AI, ML AI engineer would know about Kubernetes? Somebody has to create those YAMLs.
Yeah, so let's take a dig deep into with this particular image on the screen which is there. I think that would answer Now the question on the right hand side, you can see that we have the persona who is going to know what kind of a thing, right? Let's quickly go over it and hopefully that answers the questions. So at the bottom of it, we need the hardware, which are CPU, GPU, TPUs, DPUs, and other stuff. Um, and of course, these are being provided by the different cloud providers. So I can go to AWS and say, give me an instance with GPU, or I can go to any other cloud provider and say, give me a Kubernetes cluster which which has GPUs behind them, right? Or I can set up them on-prem as well. So this is where the SRE and operations guys are here. Then on top of it, once we have the base cloud infra ready, which are your nodes, like physical machines or virtual machines. On top of that, we are going to install the tools like Kubernetes, Kserve, OpenShift. I don't know what a case, and I don't know what are these two symbols are, but there are some softwares which are being built to uh, provide the scheduling orchestration for the AIML workloads. And this is where the platform engineer roles are going to kind of come in play. Then on top of that, we have the entire ML lifecycle in which we are doing the data prep, training, serving, doing the performance, and observing that. So all of these things is part of the AI ML lifecycle, and this is where the data ML and AI engineers are going to, I believe, work together with the platform engineering team as well. So they kind of become a communicator in a way, saying that, say, I would need this kind of infra. So if I am a data engineer or ML engineer, I would say that to run my model, I would require so much amount of CPU, memory, GPUs, whatever. And that kind of, I believe, conveyed to the platform engineer who is going to kind of provision that or give the way to auto provision that by some means, right? For example, if I would go on a portal and say I want to deploy a model, and for that this is my requirement, and platform engineer would have either created a way of auto provisioning the infra, or they would do it on the demand of the engineer. And then on top of it, we have the data scientists and developers who are going to build different models um, uh, and uh, and basically have them served by different ways, by generative or predictive ways. This is how it would look like, I believe. Any further comments? Uh, Anyone has on this? Okay. Hopefully, I was right in that case.
I think Claudia is trying to speak, but Claudia.
I don't know. Is that working by any chance?
Now we
I
can
can
hear
hear you now. I can hear you now.
Okay, yeah, I'm sorry, I'm having troubles with laptop is kind of
No worries.
yeah, so I think how you interpreted this image is correct, and it's also good because this means that the image makes sense somehow. I could maybe like report my personal experience because I lay in this picture with my day-to-day job. So I am a platform person, and when you were saying that the data MLAI engineer should cooperate with the platform engineer to figure out how to run their jobs, that's what is happening. At least in my experience, being I guess I am a platform engineer in this picture, and we've been running training workloads on OpenShift, using also ODH and OpenShift AI, and there is a continuous interaction between platform engineer and data engineer for how to run those workloads. So the platform, whatever is from platform engineer down, that's the bunch of people who need to know the infrastructure. Data engineer seems kind of in between the two, the top, like that data scientist and the platform, because it kind of has to have at least a minor introduction to the infrastructure that they will have to use. Let's assume it's Kubernetes. I think, this is my personal opinion, need to know at least the basics of how the infrastructure is running, or I mean, not even just running like hardware and stuff, just the execution model of the platform, because there has been like a learning curve from data engineers coming from on-premises. Like what I've done in my entire life was Slurm, for instance. And now it's like, oh, where is my home directory? Like there is no home directory now. It's like there is a shift that has to be done from like whatever you've seen before and what is now in the cloud native landscape is like, you have to forget whatever you've seen before and be like open-minded with this new microservices models that can be successfully used to run training workloads and inference workloads. So there is, the second and third layers, they need to cooperate, or at least that's what I've seen in my day-to-day life. But the platform engineer is the one who has to facilitate the interaction of the data engineer and data scientist with the platform, which is not necessarily an easy job. And also providing abstractions for the engineers and data scientists to run their workloads, that's also not an easy job. But there is a lot that's being done in this area. So I think from an usability perspective, there are gaps for sure, but there are ways to make it easier to run workloads in there.
Thank you. Satish, hope that answers your questions.
Yes, it does. Thank you.
Great. So let's look at this particular diagram as well while we are on this page. So as we can see here, the AI, basically under the AI, we have machine learning, and then we have the deep learning. This is how the kind of flow is there. So artificial intelligence is the kind of a superset of all of the things, machine learning and deep learning. And then we have a kind of another set of people who work kind of primarily math and stats, and there is a kind of common intersection between the common intersection between the maths and stats and the AI/ML space. That is what data science is. That is how everything is related here, and that is why we don't want data scientists to kind of be aware of everything, because they are primarily coming from the maths and stats background, and of course the AI kind of domain knowledge what they may be having. So we don't kind of want to bother them with the Kubernetes stuff at all. We just kind of give them, hey, write your code in Jupyter Notebook, and maybe you'll have a button to kind of deploy it, and then you'll see a output of that some way. That is what I believe it's going to be. So let's kind of go back to earlier. So the evolution of the AI. That's what talked about. This particular part of the paper talks about the how does the AI has come into existence per se in a very brief terms, and what are the top few things which are happening in this space here. So as we know, it is not a new term. As you can see here, it is I believe in 56, and I think it may go up a bit more behind, kind of before, while Turing machines were, or Turing tests were kind of built. I think it may have some kind of background with that as well. But the whole idea is that with the AI, we want the machines to simulate human intelligence. That is something which you want to kind of reach there. And so there are two primary classifications for the AI that has been mentioned here, which is discriminative AI and generative AI. So the simple way to look at is, in the discriminative AI, I think if we know about our outcome, that how the outcome is going to look like, we can use this. So for example, if we know that if an email has come as spam or not, we know that from the previous knowledge how the spam looks like. And then we know that if we have got this email, this is maybe a spam, right? So we know that this is a output, we are aware of it. That is what this particular type of AI means. With generative AI, I believe the main thing is that where desired output is unknown. So for example, you want to mix two images, right? And you don't know how the image is going to look like. That is what generative AI means. So again, it's a very high level classification, which I have just mentioned. Um, Anybody want to add anything on that further?
Yeah, I'd say this discriminative or predictive AI should be used interchangeably. I think we should have highlighted that. But yeah, I mean, generative is you're generating new content. So this is where transformers and other mechanisms like whose natural language processing come in play. So net new content you're generating versus like you have either supervised or unsupervised data that you have labels for, and you're basically trying to automate the prediction of something. You're building a mathematical model, for example, linear regression. You're having a relationship between the labels and the data, and you're basically using math to predict what would happen when a certain value exists based on existing data. With generative AI, and that's basically we can have clustering, regression, classification. All of these use cases have been around for quite some time, and they're not new. Generative AI is where like you're trying to generate new content. That can be text, could be audio, could be video, could be anything. And this is where I would say data. A lot of data is needed. There's a lot of data involved. The model sizes are very large. That goes towards the deep learning part that you showed in the figure, where neural networks are included, and there are multiple layers. And so these models are usually very have different requirements. I'm not going to go into the details. Maybe that's a different section, but there's a lot of different requirements when you're looking at the two. Yeah.
Yeah, so there is a kind of table mentioned in the book later. So generative AI, something which you mentioned on the right-hand side, and the predictive AI or the discriminative AI, what was mentioned on the left-hand side. So as you can see here, this is what was here, what is mentioned here. Now if you look at this table, what Adel was mentioning is very true there, right? For generative AI, you require a lot of compute, lot of resources, while the other kind of predictive AI may require less resources, and it may be uh, overall less, what do you call say, it may require less scalability also. That is what is mentioned here as well, right? So overall, generative AI requirement is very high with respect to the resources, with respect to the complexity overall building it as well, and the network and storage requirement also very high for the generative AI. So this is definitely going to cost a lot of money, as well as the other resources what are required there. Now, coming back here for generative AI, there are two primary things has happened, which is helping us to kind of achieve the kind of complexity what we are able to achieve now. Like for example, we can basically simply say, okay, take a PDF and create a Q&A for me, right? For example, right? Take an image, take a text, and build a video for me, right? So all of these things are possible because of generative AI. And what is powering that is these two things, CNN and transformers. Transformers specifically, why? Because it kind of behave like a memory structure, like a neuron for us. So it can save the context, right? It has kind of a memory. So for example, when we ask a question or when we do something, right, it can record that and then perform something on top of it. That is what the transformers are there, and they behave like a neuron, and that is kind of primary way we are doing the GPT. So GPT is, I think, stands for generative predict pre-trained transformers. I believe so. We just recheck that. So that is how the transformers are changing, or with the help of transformers, which is kind of discovered, not discovered, invented in 2017, and that has kind of changed the way we are looking at the AI right now. Okay. Any further notes on this? Okay, fine. Let me just see that. Yeah, so what is mentioned here is LLMs are trained on a massive data sets, which can be a general one, but it cannot answer the question or to a to an extent what you're looking unless you provide it with your custom data. So, for example, let's say if you want to kind of have this LLM and you want to put your own custom data within your company, or let's say think about, I would say, let's say example of Red Hat, I would just pick it up just for a thing. So I worked there earlier, so that's what I was kind of thinking about a use case there. So basically, Red Hat has a tool called SysReport. I don't know what it is there right now, but it can collect the system's data for debugging purpose. So if we have a lot of these system reports which have system data coming from different sources, then we can put that context on top of the LLMs and get the predictive output saying that, okay, when this particular machine is going to break, for example, or what pattern we are seeing that, okay, these logs are I'm seeing um, on the on the machine, what logs I have seen for last 1 year or whatever 6 months, I can say that within next 2 months the system is going to run out of memory or run out of space, kind of a thing, right? So I believe we can add those kind of custom knowledge on top of the LLMs to make it much better for our use cases, and that can be done with some of the reinforcement learning, which is called as RLHF as well, by which we can give our um, feedback to the system. So, for example, let's say if we get some output from the LLM and which is not neutral to different people, right? So we can give our feedback and make it much more uniform. Those kind of things we can build on top of LLMs. I think I just went way too ahead, but yeah, sorry. Yeah. Okay. Yeah, so merging cloud native and the AI. So this particular chapter, I think we already kind of talked about this particular picture here, but we can just think of it another way of automation that involves using algorithms to learn and improve over time without explicit programming. So okay, so I think I should kind of read this as well. Yeah, so the idea is that it is kind of what we are talking about here is the machine learning is a way by which we can just think of a way of automation using which we can learn and improve the system over time without writing the programs as well. So somehow if we can do that, that is when our systems or our nodes or the system would become akin to humans. That is what is being mentioned here. Yeah, so we talked about this particular classification already. So let's kind of go forward. Anybody wants to add any other inputs before I move on to the next part? What is the cloud native AI? Okay. Okay, great.
I think there is a question from Mohit.
Yeah, Mohit.
Hey, thanks, Tapendra and Idil. Um, I don't know whether this is a question or an observation. I may be going a little ahead. I'm on page 10, and where the challenges of cloud native AI is being talked about. Like, I'm trying to understand essentially what is the lens through which this was went through. And the reason basically I say this thing, and don't get me wrong, is that the ML ops process, as we know for 5-7 years, that exactly is being put out there, right? The 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 context of LLMs or generative AI, and by extension usability of generative AI, only is realized when agent services task everything is comes together, right? It is not just LLM, correct? So the actual issue for a cloud native, by definition of it, AI got to be, if I may just take a small example, if you go back to your image on uh, the the classical image you were looking, yeah, like the small bit around model serving, right? I'm not even going towards model training because that's where most of the things happen, and model serving obviously is an important piece. In fact, just in model serving itself, there'll be at least 5 to 6 or maybe more ways of actually doing inferencing. It is not just called serving. We do serving just for the sake of simplicity, but it is static and speculative decoding. There is continuous batching and static as well, multi GPU modeling that goes on, single GPU optimization, and the list basically continues, right? The issue essentially for anybody to start doing cloud native AI in one of those stages is to be able to have some smarter orchestration done. And I can give you an example what I mean, and we'll bring it back to the classical way we look at this, application landscape and try to superimpose this thing onto the AI landscape. So if you, for example, if you have just three models, let's say you got three models which are of different parameters of sorts, and they have different requirement. Let's say there is a lambda 7b, and there is a lambda 12b, and then there can be a lambda more than that as well. Each of them basically are of different parameters, and hence will require, let's say take a unit of GPUs, which can be an GPU from EC2 space itself, whatever unit, basically P4, E1, or something similar you do. If we simply say that this is what is going to be my compute unit, and the orchestration got to, and we just attach it to one VM, okay? So eight cores, one VM, P4D kind of a thingy, right? 8 GPUs are there, and we got three models. The problem essentially at the serving area is, how do we optimize serving of these models considering the requirement they have inherently, and also the traffic they're supposed to serve, maybe number of prompts and other things that is supposed to be. The orchestration of 2024, especially on model serving, got to take care of that in account. What I mean is that lambda 7b will require at least one GPU for that core. Lambda 13b require at least two GPUs, while 70b will require four GPUs, but they're total eight. And absolutely everybody knows GPUs are expensive. If it is for monthly, it will take 5,000 plus, dollars monthly out it. The problem then becomes is that how do we optimize as an orchestrator of a system that is supposed to orchestrate this serving? How do we optimize the usage of our hardware? It is no longer the, I'm sorry, I may be, unpopular opinion. It is no longer the bundling of the model into one or more container images. More than that now.
Yeah, so what I was just kind of going through one of the KubeCon video, which is done recently. So there are different ways by which we can configure GPUs on Kubernetes. So Kubernetes, I'm talking about Kubernetes because that's what I have seen. I have not seen the regular way of deploying, if there is any other way. Of course, there would be. But what I've seen, what I've gone through that video, which talks about a different way we can do a scheduling, like time slicing. Then there is something called NPS, something other, some other scheduling things are being there, by which we can have maybe a single GPU, and that can serve different models at different point of time. Correct. So either we can say kind of limit our workload for a given GPU and it will run there, or we can time slice it. Some of these things are in place. Uh, at least what Kubernetes is working through. So there's um, something which is talked about here also, dynamic resource allocation (DRA). Right. So the DRA thing we can program program the Kubernetes or kind of give Kubernetes hints that how you should be using GPUs. So by doing that, we can run multiple models simultaneously on the given system, and then we can utilize it better. And of course, we all know GPUs are expensive, and we should utilize them as much as we can in the time frame what we have paid for, right?
Yeah, I mean, so Mohit, all what you said, and Nipandra, all what you said are absolutely true. There's a lot of state-of-the-art research around dynamic resource allocation, GPU sharing and slicing, and how to effectively serve models, how to optimize GPUs and drivers for serving models, quantization, distillation, and all of these things are going on to address and optimize for model serving. I think to answer your question, Mohit, that you asked, I think if I understood it correctly, but please correct me. So you want to understand the lens and the reasoning behind the white paper is particularly now. Is that what you were trying to?
Yeah, no. So I'm sure there are reasoning behind it. I'm trying to understand the reason. The only section I think I use that as an example. The section on challenges is that the challenges are a little different in 2024. These challenges, if you come back to me and don't get me wrong in this thing. If you come back to me in 2016, I'll say yes, absolutely, this is all good, right? But 2024, this is, I'm sorry, this is outdated right now. Yes, we do need something like a feature store serving in the interest, especially in the open source ecosystem, since the feast doesn't work, and now we got possibly, at least in my mind, feature farm kind of a thing there. We're looking at essentially some sort of a feature serving from vector store and things like that, at least to make. So we got two challenges at hand. Can we serve embeddings and vectors faster at cheaper cost, thereby in ensuring that LLM's cost at the serving level is optimized or at least lighter, so we don't have to bundle everything, all sorts of things into a model and make it absolutely bulky, and we need a beast of a GPU to handle it. But all I'm saying essentially that my point is that the challenges are different. The challenge is not what the document says.
So let me clarify that. When we say AI, we don't necessarily mean just generative AI and large language models. So if we go to the diagram again, Nipandra,
Sure.
that there is, the circles here are important. Like artificial intelligence includes machine learning, which includes deep learning, right? And there's a lot of, the spectrum is so wide, and this paper is not just addressed. It's meant to survey the landscape, develop in language for people to talk about AI and machine learning, whether it's challenges that we've been facing all the years or the newer challenges around embeddings and context and transformers and vector databases and serving of large language models. And so the personas, who are they? How did they change? The stack, what stack is involved? And then I think not think, but there is a lot of details and the challenges around, highlighting first of all state of the art, and then outlooking more around the user experience. How can all of these components fit together so that someone like Claudia, who's a platform engineer, can build for the data scientist and for the developer to solve for the problem? So this is really not focusing at this point into, let's say, LLM serving per se. It's developing the foundation of which we have other papers to talk about challenges and zoom in serving and zoom in concrete real problems, including, the zoom in dynamic resource allocation has been alpha for quite some time. Should we put it in Cube? There are other runtimes available. There are other schedulers available. How do they fit in the picture? And so, but this is meant to, because we didn't have a cloud native AI paper before, so it is more mandatory for us to review state of the art, highlight the challenges pre-existing and today, and opportunities for the future. And then, there's a lot of room for us to grow in the community and in the cloud native ecosystem to zoom in into particular problems like LLM inferencing, LLM serving. And there we have more and bigger problems to talk about, like, how do we optimize hardware, and how do hardware vendor build abstractions for people to deploy models and so on.
Absolutely. Thanks, Adil. Nipendra.
Thank you for answering that. So Gavin has one more question. Do we need a clearer way to breaking the AI/ML use cases down into structural topology? We can reference this terms in drilling down into specific AI/ML challenges. So I'm sure I did not get the question.
Yeah, hi guys. Yeah, it's been really interesting discussion. I guess we're all at different levels here in terms of our AI and machine learning, and I'm certainly in the novice category as well. I just noticed in terms of the conversation, this is a really useful diagram, obviously, and it's promoted a lot of discussion. But when we take this next step, we start talking about specific use cases, and then the challenges that we have in terms of the technologies available in the infrastructure, it can get a little bit confusing for the novice. I'm just kind of thinking aloud here. I'm just kind of wondering if there is a way of being able to, because we're trying to map this back to Kubernetes and infrastructure at the end of the day, right? I'm a platform engineer. We're all platform engineers. So, we've done, at least I'm not on this call to become an AI machine language expert, because we've already got them on the call. What I'm here for is to understand, to provide, CNCF, perfect organization to do this, right? Is to put a structure together so we can classify and develop a topology to try and identify the requirements of these very specific different AI and machine learning use cases without having to understand, the complete details of each of these use cases, because we've got Mohit and, obviously a range of experts. Do you see what I mean?
Yes. So one of the challenges is, first of all, getting the terminology right. People don't understand. Let's say if there's a lot of jargon nowadays with LLMs, like people talk about RAGs, people talk about NLPs, people talk about transformers, people talk about all of these terminologies. I think clarifying these was also one of the intentions, and highlighting where these things are positioned when we put them in layers. And this figure, by the way, is inspired by the OSI stack, networking stack, where they have the application transport and so on. But the persona was actually added. The personas were actually added later, but they add more context to, like, you as a platform engineer, what are the challenges, and the figure or the lines here connecting to the different parts of the diagram are more like what Claudia was saying. Like, the platform engineer should initiate the discussions, data and AI and ML engineer, but should also be able to abstractly use APIs using Kubernetes and the DevOps knowledge. And there's a lot of knowledge in the platform engineer. So today, this paper is meant for everyone, to cover a wide range of topics, from ML, AI, and what we've been doing, what we're doing today, and what the new bus is about. And newer papers, so what we're doing is we're working on a landscape. We're working also on a radar. Like, how can we zoom in to a particular set of use cases, and which of these tooling makes sense for each of these use cases, so that someone who's approaching the problem fresh doesn't need to know everything, but they know that they want to solve this problem. So we basically going to guide them through, okay, if you're, let's say in telco or want to deploy something at the edge, or you want to develop a health monitoring tool using predictive AI or using a natural language processing to assess the psyche of a patient, for example, here's the stack that you need to look at for your use case. So this is one of the goals that we have. It's a bit an optimistic goal, but one of the goals that we have to kind of like distill this whole long white paper into concrete use cases, and we're still brainstorming on how to efficiently do that. I'm not sure if that kind of like touched on your points, but yeah, let me know.
Absolutely. Yeah, I mean, obviously, there's many layers behind this, and we're trying to plow through an awful lot in 1 hour. Hopefully, there'll be we'll have follow-up sessions, and we can give each of these areas that you were just talking about due justice.
Yeah, we would definitely need more sessions for sure. But as just to put a lighter note there, given as we kind of as a platform engineer, we want to kind of use Kubernetes. We have forced developers to learn about pods, what is deployment, and so on, right? We should also kind of go back to a higher level and understand what all of these things means, just to kind of get a feel of it. And then, of course, we go back to our main persona and then do all the platform engineering job there. But of course, we need to understand from the other perspective as well what are these terms, right? And then I think that requires to put up some efforts right now, I believe. Yeah, but of course, over time it will become clear. Yeah. Okay. Okay, so I think we are over the hour. It's already 2 minutes past 9 p.m. for us in India. And I think we are just on our page, I believe 7 or 8. So I think we have to continue for the next session for sure. I'm not sure whether Adil you can join the next session, but hopefully someone else can join. But hopefully the session was useful for others, and we may take it maybe at least one more week to kind of cover it up. Right. Yeah. Any closing thought for today? Yeah. Else we sign off. Thank you, Adil, and I believe Claudia and Joel, right, for joining the session from the authors team. Yeah. Thank you.
Thanks, Nipendra. Thanks,
Thank
Adil
you.
and authors, and thanks everyone. Yeah.
Thank you, everyone. Bye.
Hey, Mohit, you had a comment?
Oh, I had a comment. I thought I'm late. I thought you were saying goodbye, so I just put it down. Do we have time for 30 seconds or something?
Yeah, please go ahead. Please put your comment. That's fine. That's fine.
Could you help reiterate the goal for the group in the subsequent sessions? And by the way, I got it from some LinkedIn note. It was not in my mailbox or something, so I kind of randomly had a time and I joined. I would like to join again, but just wanted to understand the charter as we go along.
Yeah, so it's a weekly book club that we host, right? So Nipendra took the initiative, and we meet once a week on Thursdays, 8 p.m. IST. We started with a book called Production Kubernetes. It took us like good 8 months to finish that book. And this is the second book, you can say. It's not a book, it's a paper this time. So yeah, I mean, this is usually the way we conduct these meetups, right? So there's one lead who kind of drives the session, and it's mostly discussions that happen in this group.
Thanks, Craig.
Yeah, so I believe you will get a follow-up email once we like as a reminder email next Monday. You will get it, and then you can join the RSVP again for the next session. So it's not that you RSVP once; it stays throughout. It RSVP for each session, so that's going to be there. Yeah. Okay. Thank you, guys. Thank you, Adil, for answering all the questions. Thank you. Bye bye.
Thank you.
See you next week. Bye.